Hey, happy Friday, everyone. Welcome to Science Friday number 6. This week we're going to talk about something that's fundamental to all good science, or actually science in general, and something called the scientific method. Now, most of you at some point, probably in elementary school or middle school, encountered the scientific method in a science class somewhere, and they taught you 4 or 5 steps and said, this is a scientific method. And in the real world, it works a little bit differently than it probably does the way they described it to you in that class a long time ago. And that's what I want to talk about today, the practical application of the scientific method, what it's good for, why it works really well when people follow it. As all of you are aware, I'm a critic of science these days. I was a scientist myself, but I am a big critic of a lot of modern science. And one of the reasons that I'm so tough on a lot of the stuff that I see these days is a lot of people have abandoned the scientific method in favor of what I consider to be advocacy. So let's go down through the steps and let's talk about this a little bit. So the very first step that they talked to you about a long time ago in grade school was a hypothesis. That's the first step of the scientific method. And a hypothesis is really just a highfalutin way of saying you're going to state an idea, something that I want to test, something that I want to investigate. If you're a scientist, you have an area of interest, and, in my case, it was optics and acoustics, and there might be something that I want to investigate along those lines. Building a laser, seeing if you could build an ultra-short wavelength laser, which is something that I did in graduate school. So you come up with an idea, a hypothesis, and you talk to your peers about this a little bit, and generally, you'll do a little bit of brainstorming and fine-tune that hypothesis. And the reason that's important is because the very next step is to go out and get the money that it's going to take to do the research or the experiments that you need to do in order to test your hypothesis. So the second step they probably didn't tell you anything about in 6th grade. It's the funding step. No bucks, no Buck Rogers, as they say in the movies. So you have to acquire some money somehow in order to either do your research or to perform your experiment. That stuff's not cheap. Even if you're at a university and you have a lab, you got to pay for the lights, you got to pay for lab assistants, you have to pay for equipment. And typically, you write grants of several $100,000 to maybe millions of dollars to perform some experiments, depending on how complex they are, to do research. If you're going to do research, you got to pay research assistants to help you out. So these things don't happen on the cheap generally. The easy stuff, for the most part, was done a long time ago. So the things that you're trying to do now require a lot more expertise, and they're more sophisticated experiments, so they're probably going to be a little bit more expensive to do, at least in physics, in my area of the world. So you go out, you try to shop your hypothesis around to see if someone will fund it. Now, there's all kinds of ways that you can get money to do things. If you work at a university, sometimes there's internal grants, so you don't even have to go outside the university. You can get funding from your Office of Research. In science, in hard science, you can go to the National Science Foundation, you can go to the Department of Energy, Department of Defense. There's all kinds of government agencies that will fund a lot of work. And then there are some private organizations that will also fund your work. Now, not all funding is considered to be equally kosher, so to speak. If you're getting money from the National Science Foundation, people like that, that's considered top-tier kind of stuff. If you're going out and you're getting funding from somebody that basically wants to advocate for something, that's considered to be slightly less salient, shall we say. So where you get your money from, is going to eventually inform a lot of people of maybe how good your research actually was. If you take money from a tobacco company to prove that smoking's not bad for you, well, right away, a lot of people are going to look at that and go, well, I wonder what kind of a conclusion that this is going to come to. So let's say you get your money. The next thing that you're going to do is you have to concoct an experiment to test your thesis, or sometimes there's no experiment really involved. It's just a matter of doing a lot of research. So it's either of those or perhaps both, a combination of both in some cases. So you perform your experiment, typically takes a while, maybe a year or so, do your research. And my timeline was typically a year, 2 years, something like that for the projects that I worked on. Then after that comes a really, really important step. And this is probably something else that they didn't tell you about very much, and it's the data analysis step. Now, in physics and in astronomy, data analysis tends not to be that difficult because you have the ability to build machines, build detectors, build things that can acquire an awful lot of data. Point your telescope at something and just point it at it until you get the data that you need. So data analysis tends to not be all that difficult. Now, that's not always true, but it's often true. I never had any trouble looking at data sets. It was typically pretty clear that we gather enough data. We were looking at signal rather than noise, and it's not always the case, but it's typically the case. Now, that's not always true. Sometimes it's really hard to get good data. And the harder it is to get good data, the more you have to go into a sophisticated data analysis to figure out what's going on. And that's where the wheels can typically start falling off the scientific method, because a lot of times, if you are predisposed to see something in that data, and there's not a lot of data there, there's all kinds of ways you can massage data to make it say anything you want. And that's where you start running into trouble sometimes when you're doing advocacy rather than doing an investigation. The whole idea of the scientific method is to try to interpret what nature is trying to tell you about how it works. And if you go into it with a predisposed idea that the data is not going to get you off of, well, you can find anything you want in data, especially when there's not very much of it. And you have to make some choices in how you're going to go about evaluating it. So you do this data analysis step. And after that, you publish your work. And that's a requirement of any federally funded grant. You have to publish your work. So you're going to find the very best journal that you can find to publish your work in, something that's appropriate. And not all journals are good. The journals run the gamut. Some of them are top tier, good stuff. The things that you see in there are pretty good for the most part. Some of them are junk. There are journals where you can pay them and they'll publish anything you want. There's a publication called Retraction Watch, which you ought to look up. Retraction Watch tracks retracted papers from journals, and it tracks junk journals and journals that will publish anything for a profit. It looks into all that stuff. Now, Retraction Watch has only been around for a few years, and they've already got, I think, 50,000 retracted titles in their database. It's incredible the degree to which either sloppy work or sometimes outright fraud occurs in this whole step of publishing scientific work. Now, let's say you get your data, you get your experiment, your data, everything, you get it published in a pretty good journal, okay? Top-tier journal in your field. Then the next thing that you're going to have to do is wait a little while and go out and start giving presentations about this. So what typically happens is it appears in a peer-reviewed journal. Your peers get to look this over, people who know as much as you know about this, and they're going to have some questions for you. So you go to a conference and you present your paper and you give a talk about it, and typically those talks are an hour in length, and you tell everybody what you did, this is our methodology, and then you take questions. So there's peer review is a really important part of all of this. And the peer review is what sets science apart from other methods of investigating how the world works. If there were only one person in the universe, science wouldn't be possible, because peer review is part and parcel of what goes on in the scientific process. And when peer review is good, you can expose flaws in your methodology, you can expose flaws in your data analysis, your experiment, your research, all that kind of stuff. That's all going to come out in peer review as long as the peer review is good and it's honest. The reason Retraction Watch, however, has a database of over 50,000 titles that have been retracted is that peer review isn't what it used to be, especially in the sub areas, especially in the social and behavioral sciences. Peer review is just awful. It might as well not even exist. Medical science is quickly becoming the same way. Now, I've given a couple peer review talks over the years. And you walk into a room and there's a bunch of people out there and they're trying to light you up. And I remember one conference a long time ago, 2009, I went to over in Oregon, and I took my son with me and my then girlfriend. And they sat there and listened to these people like really interrogating me. I mean, they asked tough questions. They're asking you hard questions. And at the end of this, they go, why were those people so mean to you, and why are they being so nice to you now? Because we all went out to dinner and had drinks afterwards. And I said, well, that's just the way it works. They're not being mean. They're trying to ensure the integrity of work. Because what I said here, somebody paid for, taxpayers paid for all this. I made a statement that I think this is the way this particular system works. I provided some evidence for it. They're trying to help me come to a conclusion that is true about the way this system works. And that's all peer review is supposed to be. But when peer review is not robust, then all of a sudden you start running into problems. And that's what I see as a big problem in today's world. Peer review is not robust. It's lazy. People are reluctant in some cases to be highly critical. There's even cases now where authors of papers are starting to sue people who criticize them. So you do your job, you're a peer reviewer, you say, wait a minute, this stuff's no good, and here's why, and you get sued for it. That's the world that we live in now, and it's really difficult to do proper science under those circumstances. So the takeaway for all this is that the scientific method is a little bit more complex in its real-world application than you were probably taught in grade school. And if you were to ask what is the one most important step in the scientific method, I would say peer review, which actually appears in 3 places. So peer review is part of the funding process to begin with, because when you apply for a grant, you know that there's going to be a jury of your peers that reviews all these grant applications, and they kind of decide what's good and what's not. So there's some peer review there right up front. And then the publication and the presentation steps at the end of it, peer review in both those. So peer review is woven all throughout the scientific method, and it's probably the most important part of the scientific method. Having other people who know what you know look at your work and say, yeah, I think this is true. So anyway, there's a scientific method for you. That's all I have this week. Cheers, and I'll be seeing you.